Hello everyone. I am Priyanka Uttare. My topic is bias versus variance trade-off. Machine learning model often faces two major types of error, bias and variance. The bias variance trade-off describes the balance between these two errors. First, let's talk about biases. Bias is the error introduced when we use a simplified model to approximate a real-world problem, which may actually be very complex. If a model has high bias, it makes strong assumptions and oversimplifies the data. This usually causes the underfitting, where the model fails to capture the pattern. Like, for example, a linear regression model trying to fit nonlinear data will have a high bias. That means if we use a simple linear regression line to fit the data that is clearly a nonlinear, the model will not represent the data well. Now let's move to variance. Variance refers to the error caused by the model being too sensitive to small changes in the training data set. A high variance model learns the training data too well, including noise, so it cannot generalize to new unseen data. This is called overfitting. For example, a deep decision tree might memorize the training data perfectly, but when we give it a new data, it performs poorly because it has learned the noise rather than the true patterns. In short, like high bias is used when underfitting is there, like the model is too simple, wherein high variance is used for overfitting, where the model is too complex. Now let's see, understand what's the bias and variance means. Bias is the difference between predicted value of a model and the actual correct value. If the bias is high, the model makes large errors on the both training and testing data. This usually happens when the model is too simple, like trying to fit the data with just a straight line. This situation is called underfitting because the model cannot capture the real patterns. We can see in the graph, the straight line does not bifurcates the data and the underfitting occurs. Now let's see what is variance. Variance shows how much the model's prediction change when we use a different training data. A high variance model is too complex. It tries to fit every small details and noise in the training data set. As a result, it works very well on the training data but performs badly on the unseen data. This is called overfitting because the model memorizes instead of generalizing. We can see in the graph the predictions of the data on the training data set is accurate, but when we use it on the testing data, the accuracy changes and the accuracy becomes low. The trade-off in variance and biases is the balancing act between these two. Like reducing biases usually increases the variance, and reducing variance usually increases the biases. The ultimate goal of the trade-off is to minimize the total error on the new and unseen data, that is, our testing data, by finding the optimal balance between the biases and variance. The formula for finding the error is bias square plus variance and irreducible error. The graph shows the bias variance trade-off, the core concepts in machine learning. It's all about finding the perfect balance of your model. We have the underfitting zone, like here our model is too simple and has a high bias and can't learn the data patterns, so its error is high. And there is also overfitting zone. The model is too complex and has a high variance and has a memorized and training data, including its the noise, which makes it perform terribly on the new data. The goal of this is to sweet spot in the middle. This is where our model has just the right complexity to minimize and generalize the errors, allowing it to perform well on the both training and the unseen data. Now let's look at how the bias and variance trade-off works in practice. First step is model training. When we train a model on data set using algorithms like linear regression, decision trees, or neural networks, the model tries to learn patterns from the data. The second step is error breakdown. The total error or the unseen test data can be broken into three parts: bias square, variance, and irreducible error. The error from the bias square is the error from oversimplified assumptions in the model, which causes the underfitting. Variance is the error from the model being too sensitive to the training data, which causes overfitting. And irreducible error is the random noise in the data, which no model can remove. So that the total error is equal to Bias square plus variance plus irreducible error. And the low complexity model, like linear regression, cannot capture the complex patterns in the data, usually has the high bias but low variance. A high complexity models like a deep decision tree or a neural network fits the data too closely, including noise. It usually has low bias but high variance. Step three is the practical implementation. To manage this trade-off, we use several techniques like cross-validation. Validation helps us to check how the model performs on unseen data so we can detect the overfitting and underfitting. Model selection starts simple and only increase the complexity if needed. Regularization methods like L1 or L2 adds penalties for the complexity, helping to reduce the variance. And ensemble methods like bagging or random forest reduces variance, while boosting helps to reduce its bias. In short, managing bias and variance is about choosing the right level of complexity and applying the right techniques to balance the both. While the bias variance trade-off is powerful concepts, there are some important challenges and limitations. First, its difficulty to quantify bias and variance directly. In real-world problems, we cannot separately measure bias and variance. So what we usually see is the just total errors on validation or test data. Second, there is no universal rule for the perfect balance. There isn't fixed formula to tell the exact point where the bias and variance are best balanced. It depends on the data set and the problem we are solving. Third, the trade-off is sensitive to data quality. If the data contains noise or irrelevant features or the irreducible error increases, this makes managing the trade-off harder. Even simple models can show high variance if the data quality is poor. Finally, we must avoid over relying on the model complexity. Just adding more layers to the neural networks or increasing the depth of the decision tree doesn't always solve the issue. Sometimes we need to go back and rethink. Maybe improve the feature selection, perform better processing, or even choose a different model algorithm. So, the main challenge, there's no one size fits all solution. Each problem requires a careful experimentation. The bias variance trade-off explains two main errors in machine learning. Bias happens when the model is too simple and underfits. Variance happens when the model is too complex and overfits. As complexity increases, bias also increases.